All right, guys. Okay, so what we have for you today is just the continuation from what we had on Thursday, and we're going to start by working through some exercises just to use these as a review questions and uh, summarize things that we have done before about the thermal expansion. Okay, so start with this. You have the concrete sections of a certain superhighway and are designed to have a length of 25 meter. All right, so that was the idea. You have a concrete block on the street, on the road, and then the sections are poured and cured at 10 degrees Celsius. What minimum spacing should the engineer leave between the sections to eliminate buckling if the concrete is to reach the temperature of 50 degrees during maybe the at noon or whatever? So that means what you need is you're just gonna sort of like lay down all the blocks here. It's not super straight, all right? But anyway, so the idea is, of course, when you set things up over here, everything happens at 10 degrees Celsius, right there, and then you assume that things gonna shoot up to 50 degrees Celsius. So you are talking about the temperature change or temperature difference of 40 degrees Celsius there. Okay. All right, and because this is like a freestanding block of concrete. When I say freestanding, it means, of course, when things get hotter, it's going to expand. But then you can assume that the expansion is supposed to go in all directions, right? Even though we look like a side view over here, it's like we just care about the length of this one. But because we know the total length that is going to change is going to be delta L. Everyone knows how to calculate this. And it's just going to be alpha L starting times the change of the temperature. However, because of a freestanding setup over here, I think it's kind of fair that you will assume that the expansion will go on both sides. You guys agree with this? Yeah, sort of. So that means you can say that on average, it's going to expand on each side half of the delta L. Okay, makes sense to you guys? Okay, because overall increase in length is supposed to be delta L. However, because you have to put these blocks next to the neighboring blocks, so it means, of course, the next block will expand with the equal amount. So that means you will also get another half of that delta L from the next block. Cool? All right. So at the end, overall, it gets back to the delta L anyway. Sounds cool? All right. So that means what you need to do is just calculate that delta L, and that's supposed to be the minimum spacing between the blocks. And you're done. Cool? All right. Oh, okay. It was just someone joining. No problem. We haven't done much. Welcome. All right, guys. So this is it. So we're just looking at this problem over here, and all you need to calculate is just a delta L is going to be the minimum spacing that you need to leave between blocks. So let's do that. So delta L equal to alpha of the concrete. You can look it up in the table, or you can search online, and then you do the initial length times the delta L. All right, L concrete. All right, if you want, I can sort of like slide back a little bit. It's somewhere around here. Here we go. It's about 12 times 10 to the negative 6. So you just plug it in there. Okay, 12 times 10 to the negative 6. So let me omit the unit here because we work everything under SI. So we assume that at the end, we're supposed to get meter at the end, all right, as a result. The initial length, they said it's a 25 meter. Let's just put it there. Okay, this one is short, so let me put it there. And then delta T is 40. That's it. It's done. Once you're done with that, that will be the spacing that you need to leave between the blocks. Okay. You're done. Cool? Alrighty. Is there any sound effect going on here? Oh.
Okay.
What's missing here?
Okay.
Oh, it's pop up. All right, it's just I can't hear it myself, but you guys probably heard that. Weird.
Okay.
Wow, something is wrong with my system for sure. Wow. But you guys hearing my voice okay? Yeah? It's so weird. Let me try again. Yeah.
Okay. Okay. Okay.
Oh, it's back. Okay. Oh, it's just something is going on here. All right, guys. So this is done. Okay, so there's no big deal here. All right, next one is more challenging, guys. Try this. I want you guys to try this one. It's gonna be, I don't know, something that you might want to try this out. It's a college physics type question. Well, it's not college physics, but it's like a physics people love to do this kind of thing. All right, so let's try this. So you have a liquid has a density rho. All right, and then they want you to show that the fractional change, when you say fractional change, it's just like you want to take the change and then divide it by the original value. So that's what it means by the fractional change. It's a delta rho, the change of the density with respect to the value of the density at that point. They want to find out, they want you to show that this fractional change for a change in temperature is given by the following expression. And they're just asking what does the negative sign really means. Okay, you want to give it a shot? Yeah? Woo! All right, I don't need that. All right, how are you going to try this one? First thing first, everyone still sort of remember this, right? Rho, the density, is supposed to be mass per unit volume. All right, fine, done. All right, we can use some symbol here, mass, and volume is just V. All right, so now that's the definition of density. Now we would like to find out what is the change of this density with respect to temperature. All right, so I just want to attack this problem like head on. All right, I don't want to put any sort of like complex thinking of anything to this. My point is this: I want to find out the change of the density. When I say the change, now I'm gonna use a little bit of calculus right here. Because we already knew that if you want to just take the delta, that is going to be like some approximation, right? We discussed this briefly last time. But if you use calculus, everything seems to be like perfect because you work under infinitesimal change. Everything's approaching zero, right? So we take, let's do like a calculus-based problem, and then we're going to turn this thing back into delta as the approximation at the end. Sounds like a good plan, I guess.
Okay.
All right, so with that, so I'm going to find out what is the change of the rho with respect to the temperature, because that's what they want. They want to find the change in density with respect to the change in temperature. So this is going to be my plan of attack. I want to figure this out. Change of rho with respect to the change of the temperature. But now the problem is this. You are looking at the function of rho. It's a function of volume. All right, mass stays constant. You say, all right, mass not supposed to change. We are not talking about relativity or anything right here. All right, so we assume mass is mass. So it's sort of like the rho is a function of V. But then you want to take the derivative with respect to temperature, right? So, all right, how do you do it? You do it through chain rule. When I do the chain rule, I do this. d rho by dv, and then I'm just going to follow by dv by dt. Sounds cool? Not bad, not bad. And with this, then you can manipulate this kind of thing in this derivatives way, or you can equally doing exactly the same thing by talking about the differential change. Just the change. So loosely speaking, all right, I think mathematicians don't like this kind of thing. So you just get rid of dt. All right, don't do this at home, but yeah, it's always true anyway. So I don't know why mathematicians don't really like this kind of thing. But I mean, the point is this. So we can say that the change in the density, just the change, the d rho, is written in terms of the change with respect to the volume multiplied by the volume. All right, for those of you that are familiar with calculus a little bit, so I think the last expression is kind of fine. Well, that's no big deal. Okay, I just figuring out the change in the density with respect to the change of the volume. So, I mean, you can do it through the chain rule, d rho by dv. All right, so once we're done with that, now I can move on. So what I can say now is d rho is, everyone knows how to do this. d rho by dv. You just take derivative of this original expression of the rho with respect to v. So you get negative m over v squared. You guys with me? Cool. So I'm just going to plug that thing in here. Okay, so everyone still remember how to do the derivative, right?
Okay.
Okay, and then followed by dv right there. Almost done, guys. Can you see? We're almost done here. All right, I can rearrange the terms a little bit because I can see that I have one m there. I have two v down here. So I can re-express like m over v. I still have v left. And now my dv over here. Now I can just use the thermal expansion expression that we did before. So dv is just beta v dt, right? Puts everything in the differential form. Cool. This one is fine. So that means I can just follow by this beta v dt in position of the dv. I'm almost done. M over v over here is just rho. That's our definition of density. So I can move this first term to the left-hand side. So what I have left is just going to be d rho over rho. I just move that rho to the left. Negative sign stays there. Now one of the v cancel. Bam, bam. And that's it. I am left with just the beta dt on the right with the negative sign there. And I'm done.
Okay.
Cool. All right. Maybe some of you don't like this kind of question. I kind of know it. Because this is like, well, this is sound like it's not a proof or anything, but it's just a verification of this and that. Yeah, but I think this is a good practice when you really want to come up with like an expression for other variables. So like this one, they are interested in the density. They want to know what is going to be the change of the density with respect to temperature, which is like, I think this is a good extension from the expression for just the volume or the length change. Now you can have an expression for the volume change if you like. Yeah. All right. So that's it, guys. So negative sign, what does it mean? Of course, the negative sign has to be there because when you increase the temperature, the volume increases along with it. So when you have an increased volume, the density gonna drop. So that means the change is in the opposite direction. Yeah. So this means higher in temperature, it's going to be lower in density. So the derivatives is going to give you a negative sign. So negative sign means it's just opposite change, opposite direction of the change. Okay, got that one? All right, so there's a question. Okay, how you get the negative m over v squared? Okay, cool. So this is what we did over here is just take the derivative of m over v by dv. And then you just pull m to the front. So what you have to differentiate, you have to differentiate this. Yeah, and if you guys still remember how to differentiate the power function, you can rewrite this one as the v to the negative 1 dv. And when you do the derivative, the exponent drop down to the front and then you decrease the exponents by 1. So that's why you end up with negative 1 v to the negative 2. And that's negative m over v squared. Cool?
Okay.
Alrighty. Nice. Okay, but that's just for fun, I think. Yeah, and if you just rearrange this in whatever the form that you like, it's just showing you that we can approximate this to the delta. That will be the end of the verification over here. All right, cool. Next, shall we? Okay, any questions? Okay, cool. All right, last one. I think this is a good one. The reason I said this is a good one because I'm using this one as like an exam question so many times, right? Because I think this is not too complicated. It's simple enough, but it's not like super simple, like plug and play. It's not like, substitute this value into this and multiply, No, this is just a little bit of steps over here, guys. So if you know how to set this up, and then I think you're done. Overall, it's just, I think the most important one is the first line when you want to set up the equation to solve for the answer. A poorly designed electric device has two bolts attached to different parts of the device that almost touch each other in the interior as shown. All right, so this is it's poorly designed. That's pretty bad. When they touch, a short circuit will develop and damage the device. If the initial gap between the ends of the bolts are given to be 5 micron, cool, at 27 degrees Celsius, at what temperature will bolts touch? Oh, what do you think? All right, and as you can see now, the bolt has been fixed onto a structure on 2 walls over here. So that means, let's say when the temperature rises, the steel bolts will expand in one direction. Does that make sense? Because on the left end is already fixed in this whatever wall on the left here. So you can expect that the steel will expand a little bit. So let me call this a delta L of the steel. Cool. And brass will do the same thing, but it's going to expand to the left because the head of the bolt is being fixed on the right side wall. So the brass will also expand. Let me call it the delta L brass. Okay. And that's it. To close the gap, these two expansions, the change of the length, supposed to pretty much fill up the space of 5 micron here. So that means your setup of the equation will look just like this. The length change of the steel, just the length, right? You just care about the length. You don't care about the other dimension. So you can use just single dimension expression over here. Plus the change of the length from the brass, very cool, is going to be exactly equal to the gap size. And you are done. That's how it is. Okay?
Okay.
All right, okay, I'll do one more step over here. So it's going to be alpha steel, the original length of the steel. So let me call L naught of the steel, okay, and times the delta T plus the alpha of brass, L naught of the brass bolt, and times the same delta T because they are being raised with the same temperature change. And that's going to be equal to 5 micron, 5 times 10 to the negative 6. All right, and the rest is just plug in the number now. Okay, so let me try that one. Okay, alpha steel, I don't want to substitute it, but you can just look it up in the table. The original length of the steel is just going to be the original length of this bolt, steel bolt. So it's going to be 0.01 meter here. Now delta T, because you want to know when they're going to touch. So let's assume that they are touching at X degrees Celsius. So the delta T is going to be X minus 27. Does that make sense?
Okay.
Cool. And then you just add this on top of the alpha of the brass. You can look it up once again. And then the original length of the brass bolt is going to be 0.03. 0.03. And then you multiply by the same delta T there, X minus 27. Equate that to 5 times 10 to the negative 6. And that's it. You will be able to solve for X and you are done.
Okay.
Okay, not bad. All right, so I hope the first topics that we just, brought up and discussed about is just thermal expansion. I think it's easy enough. The expression is all linear equation, doesn't matter. It's just the length increase or the volume increase. They all has been put in a linear form. So that's why it's so easy to use. For single dimension, you use alpha, the coefficient of linear expansion. For the volume, then you use the beta, the coefficient of volume expansion. All right. But in the regular expansion, if the expansion happens equally in all dimensions, we already saw that the beta is 3 alpha. That's what it is. And keep in mind, this is just an approximation. Okay. Okay.
Okay.
It's not like equation that's govern the universe or something like that. Okay, it's just phenomenological expression. Or okay, very cool. Any questions, guys? So far so good. It's kind of like Saturday physics for you guys. Okay, guys, it's gonna get a lot more fun next. All right, things gonna get a lot interesting when we talk about, we're going to start to creep into thermodynamics. Okay, but before we get to that, we need something. We really need something, just like what we need before back in the day of Newtonian physics. It means we need a system that we would love to use as our studying system, because I don't think we can try to sort of like learn everything from everything, right? That's too much. So we're going to start with something simple. And it's going to be not to be too simple, because if it's too simple, then we're not going to be able to understand the structure. We're not going to be able to understand the behavior. We're not going to be able to extract the characteristics of all these things that are happening. So when we look at this, physicists consider states of matter. So everyone knows matter possess 3 main states. It's either solid, liquid, or gas, right? You guys might be talking about like like a what plasma phase, all right? But don't worry about that, because plasma will happens at like an extreme conditions. So we're not going to try to do anything too extreme at that point. So we should be fine. But the plasma is just like you pretty much ionize everything. You are dealing with charged particle. Everything is so hot and crazy, all right? So forget about that. All right. So in the solid, so you guys know that the molecules or whatever particles that build up the solids, it seems to be held in place. It doesn't move a lot, even though it can shake a little bit, it can oscillate a little bit, but it doesn't really move freely. All right, that is the structure of the solid substances. But a little bit relaxing is going to be liquid. So in the liquid, all right, those particles sort of like, well, it's still not super fixed in position. They can still move around a little bit, but it's still pretty close to their neighboring atoms. Okay, so the thing is, the shape of this liquid stuff will depend on the container. All right, no big deal. But it's still pretty close by. Everything is still jam-packed and everything. Okay, now the last one is gas. Gas is, right, we assume that the particles just running around, right? The interaction between them is going to be quite small because they are far apart from their neighboring atoms or molecules. And then they can sort of like moving things around, knocking each other from time to time, blah, blah, blah. That's fine. And the volume of this gas, it totally depends on the container because it's supposed to fill up the whole space, right? All right, that's even more than liquid. Liquid is just going to fill up, I mean, not fill up, but it's just changing the shape with respect to the container. But the gas is going to sort of like, diffuse and, fill up the whole space there. Now, if I want you to pick, so which one's supposed to be a good system for us to study? What do you think? All right, don't need that one. What do you think? So probably you're going to think of two extremes, right? First thing that I'm going to cross off the list is probably liquid. I don't like that one, definitely, because, well, it's like shifting stuff, right? Shape is kind of tough to I don't know, you don't want to define this one because you have to look for the container and everything. So liquid is somewhere in between. So two choices that you might want to pick from is either you go with solid. Well, John, this is good. It's fixed. Everything is, we can assume that everything is already fixed in place and we study everything there. Or you go the other extreme. Let's just say, hey, John, gas is all over the place. So let's do this one because it's so easy. The structure is just like there's no interaction a lot. So which one do you think is better for us in terms of studying thermodynamics? Maybe you have to take a guess at this point. All right. But the answer is this. If you pick solid, the bad thing about the solid is we just saw the linear expansion give you a super, super small, tiny expansion. Right? So that means the bad thing about this one is the volume change is small. So you're losing something in the sense that you're not going to see a lot of action due to the volume change from the solid. And we need a little bit of the volume change because we assume that the system can somehow interact with the environment the only way that they can interact is just by pushing or pulling or whatever. So we assume that we would love to see volume change. So the solid cannot give us that. And that's why we're not going to pick this solid. And that's it's going to be our gas here that's going to be used as our system to study. Sounds good? So I don't know, like you guys sort of like I'm talking too much or not. But the point is this. Some of you got confused. I don't know. It might not be super confused, but maybe just like have a tiny question. Like, why when we study thermodynamics, why do we have to study gas? And this is my explanation. The reason is we want to start at some point. We want to start at some system. And we're supposed to be smart at picking a system that can pretty much showcase the thermodynamical properties. We want a system that can, show this, act that, behave this, or whatever that you can observe or you can do some experiments with. And then you gain understanding of what the thermodynamics is happening for you or for you to understand. So that's why, first thing first, we are going to pick gas system. Sounds cool? All right. And the second benefit that you get out of this is we can pretty much come up with an ideal situation for our gas, because it's simple enough for you to be able to somehow, eventually you're going to derive some equations, some expression, and the stuff that you learned before back in Newtonian physics, it's still applicable, not too complicated. What I'm saying is this. First, the real gas is still complicated. Even though we already want to pick gas out to be our system, but the real gases are still complicated. So we will still want a super simple kind of gas, all right? Even though, I mean, it's already simple in itself, but we want the simplest type of gas. Very good, very good. Here we come. Yeah, very good. So we're going to pick the one that behave like an ideal gas. You guys remember this word here? An ideal gas. So that means, what I'm saying is we're going to pick the kind of gas that, well, doesn't have any intermolecular interaction whatsoever. Even though they are sort of like, there must be some interaction. But for us, we're going to assume that, no, it's far apart. So we assume that the interaction is super low. So we're going to assume no intermolecular forces whatsoever. But by no interactions or intermolecular forces doesn't mean that they cannot collide. They can still knock each other, and they're supposed to knock each other, or they can still knock the wall of the container. They can still knock the ceiling, knock the floor. Doesn't matter. But then we're going to add the assumption to be every time that they knock, that knocking stuff is going to be elastic. Isn't that cool? The good thing about elastic collision is you lose no energy. The energy always conserved during that kind of collision. So with that, so you have like a very, very easy to deal with ideal gas that its behavior, that everything has to follow from something simple enough, because it's just a particle running around. And this particle is independent of the rest of the system because you don't have any intermolecular forces. And sometimes when they knock the wall or knock each other, you can assume that the energy stay conserved in your system. So that's kind of cool. All right. So the way that you can get close to this, even though it's called ideal, but in reality, low pressure gas and high temperature enough gas can behave pretty close to ideal gas already. Yeah, just like your friend says, works all the time. Yeah, it works. All right. And we don't want to work harder than it's supposed to be. All right. So that's our conclusion right here. I am going to focus on ideal gas to be our system that we are going to study thermodynamics from. Cool? And next, because we are talking about ideal gas, so you will be able to talk about the states of these gases. So when you want to talk or when you want to describe the states of the gases, then you need some variable. So that's why those variables that trying to describe your system is going to be named state variables. And when you throw in a little bit of constant, we always need some constants because we work on some SI system or CGS system or some systems. You need some constant anyway. So combination of those variables and constants lead you to sets of thermodynamics variable. So these are going to be variables that you're going to use to describe your system. And in this case, our case is gas. And what are those? You guys familiar with this? Pressure, no problem. Temperature, we just learned that last time. Volume, that's easy. You just make a measurement of it. So as you can see, all this stuff, that's something that you can measure in a macroscopic level. You guys with me?
Okay.
When I say macroscopic, mean like we already said, temperature is so easy to measure. Then you just look at individual molecules and measure the velocity, do the 1/2 mv square, sum them up to get the total kinetic energy of the system. No, you don't need that. Just plug in the thermometer and you're done. You will be able to tell the total kinetic energy of the system by measuring temperature. Something like that, right? So what I'm saying over here is that is a macroscopic variables. Pressure, yeah, you just measure the pressure. You don't have to look into each individual particles and then, hey, what is the force that is acting on the wall and knock back, modem changes? No, just measure the pressure. You're done. Volume is the easiest. It's the width, the height, the length, and then you're done. They're all macroscopic levels, variables. Cool? All right. So I hope I'm emphasizing enough. Maybe a little bit too much. That thermodynamics is just trying to do something in the macroscopic level, and have all those microscopic level works in something at the low level that you don't have to touch it, and then you just zoom out and then deal with this system in the macroscopic level. That's the whole point. But anyway, you still have some fine detail, of course, because you have to know like number of molecules, which can be measured as well by knowing that here last one, the number of moles. You use this in chemistry a lot, right? Because you say, okay, 1 mole, that is just a unit of saying that, hey, it's about 6.02 times 10 to the 23rd number of molecules or atoms or particles that you're talking about. Okay, so these two going to be depends on the size of your system, how many number of molecules or how big is number of moles in the system that you have. Okay, so this number right here, I think everyone still remember, this is Avogadro number, and that is a constant because Avogadro number is defined. So for those of you that doesn't like this number, I just want you to think of 1 dozen, a dozen of donuts. It's just 12 pieces. See? So the number 12 over there is just a conversion factor between dozens to number of pieces of donuts. Same thing over here. This numbers right here is nothing more than just, hey, whenever you have 6.02 times 10 to the 23rd, we're going to call it 1 mole. Okay? All right? So, right, don't think too much about this number. It's just conversion factor. All right? Even though it has some history and all this stuff, but that's what it is. Okay? And there are a couple more constants that we're going to use. And where these constants come into a picture, you guys remember this one. Yeah.
Okay.
Welcome to the equation of states one more time. For those of you that has already taken chemistry, maybe 1 or 2 chemistry before this one, you have seen this equation already. Here we go. Let me zoom in into the first one here. PV equal to nRT. This is the things that we love, right? When you pick ideal gas system, every ideal gas will follow this equation. Perfect. Love it, right? No complications. So it doesn't really matter what type of gas you're talking about. As long as it's ideal gas, we take it. Pressure times volume equal to the number of mole times the temperature, and that's the constant R coming in. This R is named gas constant. Okay, and it has a value of about 8.31 joule per mole Kelvin, on and on. All right. On the other hand, you say, if I don't want to deal with the number of mole, you can always turn the number of mole to be, because we already say number of mole is just the number of molecules divided by Avogadro number, right? That's how you convert between mole to the numbers. So what you have over here is the R and the Avogadro number. These are 2 constants. So it's going to give you another constant anyway. So this ratio will come up as another constant, and that's named Boltzmann constant. But this has to be paired with the number of molecules in your ideal gas system. Isn't that cool? I hope you see the whole picture over here, that this is what we're going to conclude about the ideal gas. Every time you are dealing with ideal gas, you can always use this expression, the equation of states. Is PV equal to nRT. It depends on what n you would like to use. If you use number of moles, the small n, you pair it with the gas constant R. However, if you want to use the capital N, the number of molecules or the number of particles or number of atoms, then you just have to pair it with Boltzmann constant. But the structures are exactly the same. On the right hand side, you have temperature. Right there. So make sure that the temperature is being used under absolute scale. Cool?
Okay.
Yeah, not bad. I think this is good. Okay. But I just want to add on top of this one, just to sort of like confine our discussion to make it a little bit simpler. We are going to only talk about monatomic ideal gas. because we want to make things super, super simple. When I say monatomic, it means it's going to be gas that has no complicated structure in it. It's going to be just like a single atoms. You can think of it like maybe helium. Maybe it's the easiest. All those inert gas, helium, neon, all this stuff. It's a single atom in nature. All right. However, if you talk about like hydrogen, H2, that's diatomic, like O2, or maybe like whatever, like complicated, NH3, benzene, or I mean, those crazy stuff, we don't want to talk about that one. Right? We're going to confine ourselves with just monatomic ideal gas. And of course, once we understand this kind of thing, the extension to diatomic, triatomic, or monatomic, the polyatomic and all those stuff can be done, even though things will exponentially more complicated. All right, so just to make things pretty sort of like, simple and clean and everything. So we're going to focus on monatomic ideal gas. Okay, that's just our agreements here. So once we have that, one consequence that you can pretty much like derive from this expression is just the utilization of this. Because every ideal gas has to follow this expression, right? So if you rearrange this equation a little bit, PV over T. So the right side of this one will be left with just N times R, small n, or is a capital N with a K. Sometimes you don't need to write down the subscript B, right? I think everyone understands it. So as long as your gaseous system that you are looking at over here doesn't change in quantity, so it means you're not adding more gas into your system, you're not extracting or get the gas to leak out. So everything is still sort of like fixed in numbers of molecules or atoms in your system. The right side stay constant. You guys with me? And that's usually the case when you are dealing with a closed system. The amount of gas stay fixed, doesn't change. So the only things that are going to change is the things that are going to change is just going to be the variable, the pressure, the volume, the temperature, blah, blah, blah. But these stay fixed. So that's why you can always say that the ratio of the PV over T will not change as long as you have the same amount of gas in your system all the time. And you can use this expression to compare between two conditions of gas. It's kind of cool. It's easy to use.
Okay.
Okay. All right. Keep this in mind. This is going to give you a background that you really need later to understand thermodynamics system and thermodynamics processes. It's going to be a lot of fun next week.
Okay.
Right, but this week we just like sort of, go slowly and see how things go. All right. Let's practice simply. Try this problem first. I think this is like a plug and play problem here. An ideal gas occupies a volume of 100 cubic centimeter. All right, so we have a unit that we need to take care of for sure. At 20 degrees Celsius, it's in Celsius. All right, we don't like that. We want absolute temperature. And the pressure is, how many fives is that? 10 to the 5th Pascal. Pascal, we love it because Pascal is already in SI system. I think you learned it from fluid dynamics in the physics 1, yeah? So they said determine the number of moles and also the total number of molecules. So what they want over here is they want this small n here and they want the capital N there. All right. So all you need to do is just, bring in the correct expression to apply. So let's start with the first one, the small n, PV equal to small n RT. Cool. All right, now let's plug in the numbers. The pressure is already given there. So let me put 10 to the 5th Pascal. That is for pressure. Now the volume. The volume is here. It's 100 cubic centimeter. I have to turn this into cubic meter. So I have to multiply by 10 to the negative 6. You guys with me with this?
Okay.
For those of you that's not, I will explain how you convert the units back and forth really easily a little bit later. Equal to N, that's what you want to figure out. R is already there. You can, look it up, 8.31. And the temperature over here, you have to use a Kelvin scale temperature. So it's going to be 273. Let me omit that 1.15 there, plus 20 to turn it into Kelvin units. And that's it, guys. You're done. N can be found this way. Cool?
Okay.
And then you can do equally the same thing using PV equal to capital N KT, if you like. Okay, so I'm gonna drop that subscript B here because we are pretty sure that there's no other K's involved here. All right, so you just plug in the number again, 10 to the 5th Pascal. On the left side is no change actually, because it's gonna be the same pressure, same volume. The only thing that is going to change is going to be this constant that you're going to plug in here. That's all. Even the temperature is pretty much the same. And then the capital N can be found. You are done.
Okay.
Okay? All right, so this is a plug and play problem. However, the unit conversion. So I don't know you guys okay with this unit conversion thing or how you actually think in your head, but my tip or it actually what I've been using all along is this. When you have centimeter cubed, okay, you want to convert this into cubic meter, right? You want to get to the cubic meter. So in my head, when I'm doing this, I'm gonna always treat all those prefixes. So that means the centi is 10 to the, oh, sorry, not multiply. Centi is 10 to the negative 2. What else do we have? Milli, 10 to the negative 3. Maybe micron, micro, 10 to the negative 6. You can have nano, 10 to the negative 9. You can have kilo, 10 to the 3rd. You can have mega, 10 to the 6th. On and on, right? Whatever you have. All those prefixes. I will always treat these prefixes to be just a number. You guys see what I'm saying over here? When I say treat it as a number, look at this. This is centi multiplied by the m, the meter. So in my head, this is nothing more than just 10 to the negative 2 multiplied by m, the whole thing cubed. You guys with me? And then you can manipulate this just like you manipulate numbers. So that means I can pretty much partition this here. See? And that's why I know exactly it's going to be 10 to the negative 6 cubic meter. That's how I convert between units. All right. And by doing this, it's so easy for you to convert units either from small to big or big to small. It doesn't matter. For example, if I start from, let's say, meter cube, and somehow you really want the nanometer cube unit somehow. Okay. So what I'm doing over here is what I'm trying to do is going to be, okay, I'm starting from this, right? So I'm just multiply by nano divided by nano with the m, the whole thing in the cube. You guys seeing what I'm doing here? I haven't done anything. I just multiply by 1, nano over nano. But then I just gonna pair this nanometer. That's my final things that I want. So that means I'm gonna have 1 over nano cube left in the front. And what I have left is nanometer cube on the top. That's my final phase of answer that I want. So what I have left in the front is just this number right here. So that means I know that I have to multiply with 10 to the 27 to give me 2 nanometer cube units at the end. Cool?
Okay.
Does that help? I don't know. If it helps, then use it. If not, that's fine. I think I have seen many of you sort of like come up with like, I don't know, it's like a pattern. Like, okay, if I go from big to small, I have to multiply. If I go from small to big, I have to divide. And I don't know. It's just so hard for me. I stopped doing that for a long, long time. So my point to take over here is just when you want to convert the units, whatever the prefixes that you use, you can treat that as just a number multiplying each other. That's all. And you can move things around, factor in, multiply in, divide it out. Your choice. Okay. I hope this will eliminate some mistakes that might occur during the unit conversions processes and all that stuff. All right. I don't know all right or not. Okay, guys, next. Okay, everyone try this. You have pure helium gas is admitted into a tank containing a moving piston. So now moving piston is just something that can be moved. So it means your volume can now be changed. The initial volume, the pressure, and temperature of the gas are given. All right, so that's already there. Volume, pressure, temperature. All right, looks pretty close to SI, except now you have a kilo there, but that's fine. Now, if the volume is increased, to a new value. All right, so you have new volume and the pressure is new here. All right, find the final temperature of helium gas. Can you see this now? This is just a comparison between two conditions of gas. One condition, another condition. So I can call this condition number 1. I can call the bottom one to be the condition number 2. So what I can say, I can use P1 V1 over T1 is equal to P2 V2 over T2. I think you did this back in the chemistry or stuff like that, right, in high school. All right, and the good thing about this one is, as long as you're using the same unit on both sides, you don't need to do any conversion. So what I'm saying over here is this. As you can see, the unit for the pressure is kilopascal on both. So it means, all right, you don't have to convert into Pascal or anything as long as you keep that kilopascal on both sides. Does that make sense?
Okay.
All right, that makes a lot of sense in the sense that you don't need to calculate a lot of numbers. So P1 to 200 Pascal, okay. The volume number 1, that's 15 times 10 to the negative third meter cube. Temperature is already in Kelvin. Perfect. We love that one. So it's 300 K. All right. The temperature, of course, you need to use Kelvin. All right. You cannot use Celsius. But Ajahn, you said just use the same unit on both sides. But don't forget, converting from Celsius to Kelvin, you do the addition. You're not doing the multiplication. So it's not like a conversion factor. It's just summing another constant to the number. So you cannot do the cancellation things there. All right. Equate that to the new condition. So the new pressure, that's what that's already given, 350 kilopascal. The new volume is there, 10 times 10 to the negative 3 cubic meter. And that's it. You just calculate what should be the new temperature right there. And you are done.
Okay.
All right. Not bad. All right. So, well, we're not going to have this kind of question in the exam, of course. But you need this. You really need to do this when you really do thermodynamics stuff in a little bit later. Next week, of course. Okay. All right. So, guys, I think this is a good place to stop here. First half of the lecture. And after the break, we'll just start to dive into the first things about heat. Okay. And that will be the first component that is going to be the big component in thermodynamic stuff. All right, guys. So let's take a break right here.
Okay.
And then I'll see you guys in 10 minutes. Sounds good? 11? Yeah. Okay. First. All right. So what we have next for you guys is now start to talk about something is very actually very important. It's one physical quantity that we are going to use a lot in the next couple weeks is heat. All right. And now to get things started here, I think usually I would love to start out with well, it's like, what does it mean by heat? So it's gonna be like a long story and all stuff. So I just gonna ask you, how do you feel about this one when I say heat energy? What do you think? What about this? Heat energy. You feel all right? Or it's just like, not bad? Or it's just like, not good? Or something weird? It's like fishy? Something like, it doesn't sound right? Or whatever. What do you think? Heat energy. All right. For those of you that would like to translate directly in Thai, that might not sound so bad because we usually call heat to be ความร้อน yeah, and energy is just energy พลังงาน. So if you translate this one directly, you might gonna get to the word of พลังงานความร้อน which is not good because in physics or in English actually, so what you really want to use is more like a thermal energy. So it's an energy that related to something thermal, something temperature, right, or something related to that. So this is not good. So you will never use this word ever in your life, or you shouldn't hear anybody using this one. Heat energy doesn't make any sense because heat is energy transfer. The key is transfer. Transfer. Seriously. All right. So what I'm saying over here is what you really, really want is saying this thing using the original definition of this. So it's the energy transfer energy, which doesn't make any sense, right? So you're not having to have energy to do the energy transfer. Well, but when I say it, it doesn't sound so bad, yeah? Yeah, you probably need some energy to transfer energy, right? Okay, but no, not that sense. Okay, but the idea is this. Heat itself is already signifying the energy that is already transferring. So you want to talk about the energy that gets transferred. That's you call it heat. So that's why every time we talk about heat, usually you talk about the flow automatically. There is some energy movement going on. So that's why it has some dynamics built into this word. Okay? So just to emphasize one more time that heat is not the energy contained inside a body. It's like now, our body temperature is 37 degrees Celsius. So because we already know that if you have some temperature, it means you have some built-in energy in yourself. You have net total kinetic energy in your body. So that's why you have non-zero Kelvin temperature. Does that make sense now? All right. So that means when me have the temperature of 37 degrees Celsius, so it means we have thermal energy built into us. Molecules and stuff in our body is shaking a little bit. Okay, there's some movement there, there's some kinetic energy there. So that's why you have non-zero temperature. Okay, and because just to keep saying that, hey, we have total kinetic energy in your body, blah, is gonna be long. So eventually they come up with the idea, just say, hey, the energy that contains inside the body that you can pretty much measure through some temperature or your thermal energy will always mean internal energy. So that's mean you can think of the internal energy to be the summary of, the sum of every kinetic energy that you have in your body. Does that make sense? Okay, so we can skip talking about like the total kinetic energy of your system. We just call them internal energy and be done with. All right. So now you sort of get this, some idea that, okay, so in the future, you will see that the internal energy eventually will link to the temperature. You cannot escape from this. You cannot avoid this because we already know that temperature links to the energy of the system. All right. Okay. But now let's turn our attention back to heat. So now heat is energy transfer. So here we go. Spoiler alert. Have you heard of this energy transfer before in your life? Maybe somewhere. A little bit of encouragement here. Okay. Any energy transfer have you seen before in Newtonian physics? Any physical quantities related to energy transfer that you have already learned before, calculated before, have already done something. K2P, what is that? Oh, okay. Kinetic energy to potential. All right, very good. That is the energy change, right? It's a conversion of energy from kinetic energy to potential energy. But that is not a transfer just yet. You guys with me? Or collision, that's good. Collision is sort of like there's some energy transfer because you have some interaction and then you transfer the momentum. So when you transfer momentum, then you get the energy to get transferred. Very cool. All right, so let me point out the first one first. When you do just the transformation of the form of the energy, now you have to know this. Let me draw this one. When you drop a ball from some height, down here, you get some velocity, right? 1/2 mv squared. You started out from mgh. Can you notice something here? Getting from the top to the bottom, you are not transferring anything to anywhere just yet. Cool? Okay. Not yet. So in this one, it might not be saying that you have any transfer. It's just changing the form of the energy from potential to kinetic energy. All right. But the collision is a little bit better. It has a better sense of transferring because you might have object A knocking onto the object B. And then after knocking, Then you transfer some momentum to it, and that means you transfer some energy to it. So that's kind of good. So you see the difference here? You want the energy transfer. But there is another one that actually give you like a perfect sense of transfer. Perfect sense of transfer. The reason is because with the collision, you can still treat this A and B to be the same system. Does that make sense? Because when you do like conservation of momentum, you assume that particle A and particle B that are knocking each other are within your system. So if you consider the whole system, there's still no transfer. It just exchange between portion in your system. So it's not totally a transfer just yet. So what else, guys? One more. There's one more that actually give you the definition of energy transfer perfectly. You transfer something to the system actually. So that means there must be something that doing from the external stuff and transfer something to the system from the outside. Any participation here? Power. Okay, very good. Very close. So the power is very good. Energy per unit time. But then you can say about the energy transfer to be work, guys. That's what I want to get to. Thank you.
Okay.
Work. W equal to F times delta S. Remember this one vaguely? Okay, there's a W here. So when you drag something, you pull something, you push something, when you say force, that is force from the external stuff, something outside the system. So that's why this is a work done by the external force, something like that. See? So when you push something, you transfer the energy from you, who is pushing it, to the object that you're pushing. There is an energy transfer there. And then if you talk about that object to be your system, so you get some energy from outside. Okay? So this is going to be the story of thermodynamics next week. Today, we're going to focus on heat. And next week, we're going to bring in work, and we're going to combine them into the grand thermodynamics law. So stay tuned for that. Okay?
Okay.
I don't know, is that I'm maybe detour too long here? But my point is, I want to emphasize on this word is energy transfers. Both heat and work are transferring of energy. So there must be some flow. There's some, exchanging of the energy from system to outside. That's the clue. Okay. Now let's come back to our business of heat. So in terms of the units, of course, we have SI units of joule. You use that all the time. But then because every time we talk about heat, I think maybe because this subject is so old, you have another unit that's still being used today. It's called calorie. And the conversion factor between the calorie to the joule is 4.2. So 1 calorie is 4.2 joules. Okay, so we use that one a lot, calorie. And James Joule himself is the one who shows that the heat that physicists or scientists back in the history that they got confused before. At first, there's no understanding about what is heat and what is energy. All those stuff are sort of like still not the same thing. So there was the time that energy is still like a very loose concept. People still don't understand what does the energy means or what kind of connection with the work, energy, and heat. So at the time before Joules show up this experiment, they thought that heat and energy are separate things. But then this experiment just sort of like put everything to rest. This is just like an experiment that you try to, he drops a big mass onto a ground. So you know that there was some height there. So that means you start out with the mgh energy on both sides. And then he dropped these two big masses down to the floor. And this two masses attached to a paddle that can sort of like turn the water in the tank. And then he can measure the temperature change. And it turns out you can pretty much like do the calculations that how much energy is being input into the water. And you can observe that by the increase of the temperature. Does that make sense?
Okay.
All right. So even though nowadays experiment looks so simple, but back in the day, this is a huge experiment. So these experiments by Joules just show that the mechanical energy can be pretty much transferred into something else. And when you do something else, it can also turn up in terms of the temperature change. It doesn't have to be just within the mechanical stuff only. Okay, cool. So that's why with this experiment, you get this conversion factor right here. Okay, so the calorie units, that was the units that they used to study heat using mainly water back in the day. But then once you have these experiments, well, oh, okay, calorie or joules, they are pretty much the same thing. Okay, one fact, just so you know, the calorie that we are talking about is not the same as a calorie that you use in food packaging. Here we go. When you look at the food packaging, the calorie over there is a capital C. So that means it's equal to 1,000 calories that we are talking here in class. Cool? All right, so when you eat something and it's a 230 calorie, so that's actually, you have to multiply by 1,000 to get down to the calorie that we use here. And then you have to multiply by, or actually you have to divide it by 4.2 to get to the joule, on and on. Oh, you have to, multiply by 4.2 to get to the joule. So if you look at the food packaging in, I think mainly in Europe, in EU or whatever, I think they're good. They give you 2 units already for you. That's kind of nice, right? So you don't have to do the conversion and stuff. It's already given in kilojoules for those of you that prefer metric system or SI system, and then it's already given in kilocalorie. They don't even use capital C there. They just write out saying that it's a kcal. So this is a very scientific nutrition level and all this stuff. That's nice. Okay, but at least this is clear. You can work under whatever unit. It's just conversion between units. There's nothing new. Okay? All right. Now, so what does it do? What does the heat eventually do? The answer is, of course, Ajahn, if you transfer some energy to a system, if the energy of the system increased, the temperature has to increase. That's a simple consequence of the understanding that we have been building up to this point. So what you say is, at least you have to tell that if we use Q to signify the amount of energy transferred as heat, so we're going to use Q for heat, it's going to link to the temperature change. You guys with me? All right. So that makes sense. So I can turn this one into an equation by give it like some constants in the front. But then when I put in the constant in the front, that constants behave in a way that it gives some property of that object. What I'm saying over here is this, guys. Think about this. If you give some energy to an object, that object has to increase in temperature for sure, right? But then you say about that, it depends on the object. Some object might have a big increase in temperature. Some object might not have that big of the delta T. It depends on how that object can store the energy. You guys with me with this? One more time. So think about this. If you eating something and there is some sort of like a scaling that give you the fullness, like I'm feeling full, and somehow you have a degree of fullness, think of it like a temperature, right? So you have a degree of that. So when you eat a little bit, so of course you increase the degree of fullness in your stomach. But then if you have a very big stomach, so before you feel full, you have to eat a lot of food. So that means you have a big food capacity in your body. Does that make sense? But on the other hand, if you have a very small stomach, so that means you only eat a little bit, you already, all right, it's already full, my whole scale of my fullness, and I'm already full. I don't want to eat anymore. So for those that has a small stomach, that means you have a very small capacity. Same thing with the heat, because heat is the energy transfer. So your stomach is like your energy storage. So there will be some substance that can store a lot of energy. If that is the case, you will observe a very small rise in temperature because your storage is big. Before you can fill up the whole storage, it would take a lot of energy to fill in. Does that make sense? On the other hand, if some substance has a very, very small storage, you only put in a little bit of energy, you already fill up the whole storage there. So this means the temperature rise will be big. So that's why the interpretation of this constant over here is called heat capacity. Is your size of your storage. Is this capacity of energy in the substance. Or think of it another way is, of course, is you given the same amount of Q, you transfer the same amount of energy to a substance. The substance with big C will have a small delta T because the product between C and delta T stay fixed, equal to Q. But of course, in comparison to another one, you might have a very small C, so you must have a big delta T right there.
Okay.
I don't know if this writing makes some sense or not, but that's what I'm trying to explain, that, okay, the delta T depends on the heat capacity of that substance. If the substance has a big capacity, of course, you're not going to see a lot of delta T there, okay, and vice versa. Cool? All right. So with that in mind, you still have a problem here. Well, I kind of get it. It's a heat capacity of a substance. But then the problem that's kind of like not very convenient to use is this. If you bring in a water, okay, let's say it's like a gram of water. You know that a gram of water will have some heat capacity here, you know. But then if you bring in like a, I bring in like a kilogram of water. It's not drawn in scale here. All right, it's not going to be way bigger than this, but that's the idea. Everyone know this 1 kilogram will have a bigger C than this 1 gram because 1 gram is so tiny. But then you come up with the question, so, but they're both water. Shouldn't they have the same, some kind of like some parameter or something that related to heat capacity? Yeah. So that's why for you to be able to build something that not depending on the amount or depending on the size of the substance that you bring in, you're supposed to define something that depending on intrinsic property of that material alone. So that's why physicists introduce another one. It's a specific heat. So it's going to be the heat capacity just like before, but you do it per unit mass, or in our case, per kilogram in SI system. Cool? So with that, then you don't mind how many gram of water or how many kilogram of water you're going to bring in. As long as it's water, you can say, okay, Dan, look at this. Right there. You always know that every 1 kilogram of water, it will contain, or it will have the heat capacity of 4186 joule per kilogram. So every 1 kilogram, it will have heat capacity of 4186. Cool? Or if you bring in a gram of water, that's 1 calorie. See? And then later, if you bring in 1 gram, or you bring in 1 kilogram, or you bring in m kilogram, all you need to do is just multiply that m with the specific heat. So we use the small c to represent that specific heat. So it's a heat capacity per kilogram. And how many kilogram you bring in, you just multiply that. You get capital C back. Sounds cool?
Okay.
All right, so I hope this is sort of like clear things up. Physicists or scientists love to do things that's not depending on the amount of the system. They just want something that pertain to the intrinsic or pertaining to the property of just the type of substance. Yeah, not the amount of substance. Okay? All right, guys. So this is cool. So we can conclude that we can write down the equation that link between the amount of heat transfer, okay, the amount of energy that get transferred through heat. Well, okay, I'm just saying confusingly. Sorry. I'm just saying that the heat, the Q, which is already the energy transfer, equal to mc delta T. And you are done right here.
Okay.
All right, guys. I think this is, maybe I introduced this too long, but you have seen this maybe from middle school science already, I think, because I think this is one of the subjects that we study in science, because it's kind of like equation is easy enough. You can have like an intuitive idea of how things will change with energy that get in, and the temperature has to rise on and on. It's kind of easy to get connected to. So in Gen Chem, one final example. Okay, cool. So you see, you have seen that before. Okay, so this is going to be our main equation every time that you provide some energy to the system, and the system has to change in temperature. Q is equal to mc delta T. All right, and then you can refer to this table, or you can look it up on Google to figure out what should be the specific heats for the substance that you are looking at. Cool. All right, guys. Now, just starting out, we're gonna try to do some examples over here. But before we get to that, let's answer just like a quick question here. Just double check your understanding here. You guys going to the beach? You're going to a beach there. Of course, the main two substances there just sand and water. During the daytime, okay. All right. Now, can you conclude which one has a higher heat capacity? Or, I mean, specific heat actually. So sand or water should have a bigger specific heat. What do you think now? Just make sure you get it right. Yeah. What do you think? Sand or water? Sand or water? Just make sure that you got it right. Sand or water? Sand or water? All right, okay, you don't need to type it in. All right, but at least you have to think in your head. And the answer is very good. It's gonna be water. Okay, so just make sure that you get that answer in your head. The reason is because, of course, when you're standing on the sand, your feet will feel a little bit harder than when you walk into water, of course, right? And the reason that the water is cooler than the sand is because the heat capacity or specific heat of water is bigger. So during the daytime, they both receive energy from the sun equally. But the reason that the sands feel harder to your feet is because the specific heat of sand is smaller. So that's why the temperature change is higher than the water. Cool. And if you come back to this table right here, you can see water is pretty big substance, pretty big specific heat substance right there. In comparison to, for example, like aluminum, maybe what else do we familiar with? Iron, glass, okay, wood, marble. See, all those stuff has smaller heat capacity or specific heats than water. So in this table, it turns out water is the biggest substance. I mean, the biggest specific heat value substance right there. All right, guys. So just to make sure that now you understand the whole relationship between the heat, the Q, and the delta T. All right, everything rely on the specific heat of that substance there. Okay, let's take a look at plug and play question, shall we? The temperature of a silver bar rises by 10 degrees Celsius when it absorbs 1.24 kilojoule of heat. The mass of the bar is given. Determine the specific heat of silver. See, this is plug and play problem. You just like, okay, no problem. Q equal to mc delta T. You want to figure out the C is going to be Q over m delta T. The Q is what? There you go. 1.24 kilo. You can turn it into joule if you like. Okay. And then divided by mass. Now it's in gram. You want to turn it into kilogram. That's no big deal. Divided by 1,000, you get a kilogram. The delta T is rises by 10 degrees. So it's just 10. You don't need to change anything because the change in Celsius is the same as the change in Kelvin. So it's still 10 anyway. And that's it. You're done. Cool. All right. You can just fill up the rest yourself. All right. That's plug and play problem. But the thing is, things gonna get more complicated in this one, which is not very complicated, but I think I like this example because it's very realistic and people apes into solar collector more and more, right? It's getting cheaper, right? But it's still expensive anyway. All right, so you have a solar panel that you are going to use to operate a water heater. So you have a water heater operated by solar power. If the solar collector has an area of 6 square meter, so you somehow come up with a solar panel 6 square meter. Okay. And the intensity, even though you don't know this word for exactly what it is, but at least it's something that you get from the sun. And now you can look at the unit is watt per square meter. We're going to learn about intensity later, all right? Maybe in a month from now. But for now, when we look at the unit, this is fine. But intensity is 550 watts per square meter. Because now your solar panel has 6 square meter area, so it means your total power that you can deliver from this panel is going to be 6 times 550 watts. You guys with me? Cool. So the power is given, and everyone knows from physics 1, power is just energy per unit time. And in our sense over here, energy that we're talking about is the energy flow or energy, you can call it flow or transfer or whatever. But for us, this is in the sense of heat. We're going to use that energy to warm up the water in our water heater. Okay, so that is the same amount of the heat that we would like to calculate. Cool. But then they said, how long does it take? So they want to figure out the amount of time, delta T down here, to increase the temperature of 1 cubic meter of water from 20 to 60 degrees Celsius. So this means what they want is the amount of energy that required to warm up the water is going to be calculated from MC delta T. Yeah, that's a direct application of this one. First, what is the mass of a cubic meter of water, guys? All right, it's not freezing or anything. It's just me stopping movement just for it get your attention here. 1 in the unit of what? 1 kilogram? 1 ton? Okay, correct. No, not 1 kilogram. Very good. So 1 kilogram is only just a liter of water. That's 1 kilogram. But then when you have a cubic meter, so it's 1 meter long, 1 meter width, 1 meter depth, that is 1,000 kilogram. It's huge. Water is huge, actually. Yeah, so it's almost like a mass of a car right there. So that's 1,000 kilogram. That's 1 cubic meter. You have to be careful with that. Times now the specific heat of water. You can look it up from this table right there. There we go. You can approximate to be like 4,200 if you like. Okay, so make things a little bit easier to calculate. So it's 4,200. It's going to be joule per kilogram degree Celsius right there. See, I just use this approximation number right here. Okay, cool. And then you multiply by the delta T. Now you're going from 20 to 60. So the delta T is going to be 40 degree difference. With me, right? Okay, delta T is 40 degrees Celsius. Cool. And that's it. So that means you know how much energy you need to warm up the water from 20 to 40. And then you just plug this thing back in here. So that's it. What you have is the power is right there. 6 times 550 is going to be equal to the amount of Q that you have already calculated here divided by delta T. So that means you will be able to calculate the delta T from here. And you are done. Okay, not bad. All right, so this is pretty realistic because I think you use this kind of calculation everywhere. Because I think if you go to YouTube and then try to calculate like, hey, can I use solar panel to run air conditioner in our house? And then you just have to look at the spec of the solar panel, how big of the power it can generate, and what is the amount of energy that your air conditioner is requiring. And then you should be able to expect, all right, you can run your air conditioner for 8 hours on and on. All right, so that's kind of question that we love to do in real life. So it's just right there, easy to do, and it's very practical. Would love to get some solar panel myself, but I think it's still expensive though, even though it's cheaper than 5 years ago for quite a lot, I guess, but it's still, well, it's still not super cheap. Well, so at this point, it seems like you just pay your electric bill in advance. But it takes, I don't know, ROI is about maybe like 4 years or so. Yeah, I think. And I'm not so sure, like, will solar panel will last how long after 4 years? I don't know. So I just might have to wait for a few more years when it's cheaper and it's maybe the quality of manufacturing is just maybe a couple times better. And it's guaranteed that it's going to last maybe really, really 10 years with a very acceptable efficiency, then I might want to install solar panel myself. All right. But for now, it's just waiting for it. Or any of you have any connections? Just might want to give it a try. Okay. Move on. Okay. It would be nice to have, like, This lecture is sponsored by. And then for those of you guys that participate in answering some questions, then you can receive some gifts from our sponsor today, on and on. That would be nice. Okay, here we go. So the last stuff for today, guys, there is another event that might be you hitting some point in the temperature that when you provide some energy to the substance might not increase in temperature at all. You don't see any delta T, but there is something changing. It's called phase transition. All right, I think you have seen that before. So we already discussed about the gas, the liquid, the solid. So when they want to change from one phase or one state to the other, then you need some energy to do that. And during that transition from maybe solid to liquid, liquid to solid, or you want to go from solid, liquid to gas, gas to liquid, you need some energy. And during that phase transition, you won't see any delta T because it still have some activity of phase transition going on. You guys with me that? Yeah. So that means the energy that you put into your system at that point won't be showed up as a temperature change. So that's why we're going to name the heat during this phase transition process to be latent heat. So it's a heat that is been hidden. So it's sort of like a hidden heat. So you put in the heat, you won't see the delta T as you return, but you're going to see the change in the phase. So that means there will be amount of the substance that gets transition into different phase. So that's why all you need to know is just, hey, how much heat do you need or how much energy that required for you to do that phase transition? And when we want to define it, we want to define it per kilogram. Why not? Right? Or per mass. That's what we want to do. So the latent heat is the amount of heat that is needed to give that substance going through the phase transition per kilogram. So how many kilogram you have, you just have that multiplied with the L, you will be able to calculate the total amount of energy that you need for that phase transition. Does that make sense? All right. And the table will show you that numbers. For example, all right, we probably familiar with the most with water. So look at this. There is the latent heat. Now look at the name. The latent heat of fusion. From the sound of it, it's something that, is fusing. I don't know. It's when you are changing from solid to liquid. That's the heat of fusion. But if you want to go in the opposite direction, you can name it as a liquid to solid. It's called solidification. Okay. On the other hand, you might have liquid to gas. So everyone seems to familiar with this. Is a vaporization. On the other hand, on the way backward, you can go from gas back to liquid. You can call it condensation. All right. Okay. So that's pretty good. So let's come back to here. So solid to liquid or liquid to solid, they will have the same value of L. It's just different process going forward and going backward. You guys with me? All right. So the L over there, it's just showing right here. So it means water need 3.33 times 10 to the 5th joule per kilogram. So every 1 kilogram of water will require this 3.33 times 10 to the 5th joule for it to change the phase, either from liquid to solid or solid back to liquid. Cool? All right, so that's what it means by latent heat. And then you have the same thing with the latent heat of vaporization. So as you can see, every 1 kilogram of water, you will need this much, 2.26 times 10 to the 6th joule to vaporize a kilogram of water. Or on the other hand, a vapor of 1 kilogram will release this much energy to condense back down into liquid water. All right, so that's what it means by latent heat. Is the heat of, it's a heat during the phase transition per kilogram. Okay, so you can calculate the amount of energy by using just M times L, and you are done. Okay, so this is a hidden latent heat. So overall, I just want to conclude these two expressions. So in conclusion, you have Q equal to MC delta T. Every time that you don't have any phase transition temperature, you're going to have to be able to see the delta T along the way every time you supply some energy to your system. Or if you hit the phase transition temperature, you're not going to see any delta T, but you're going to see the phase transition. All right, so I'm just going to use water to be our example over here. And let me start right from the super duper super cold ice. So it's like ultra frozen ice, negative 30-degree ice. So it's deep freeze over here. And now in the horizontal axis, it's just the energy added. So let's say you just constantly adding the energy to your ice and see how things goes. So first, during the initial states, because it's already negative 30 and it's still under zero, so this ice will get hotter and hotter. Get hotter. It's still pretty cold anyway. But anyway, the point is, all right, you're going to raise the temperature of this ice higher and higher from negative 30. All right, so over here, you will be using Q equal to MC delta T. Does that make sense? Right? Because this portion doesn't have any phase transition. And the C that you're supposed to put in here is supposed to be C of ice. And of course, the specific heat of ice is not going to be the same as the specific heat of liquid water. They are different. Yeah, they're not the same. But now, once you hit 0 degrees Celsius, that's when you know the phase transition will start to happen. So ice will start to melt. So during that phase, you won't see any change in temperature anymore. So it will be flat at 0. But then more ice will get melted. So now you have a mixture between ice and water. Okay, ice keep melting until ice completely melt. That's what you have. So during this portion over here, you just have to use Q equal to ML. Okay, and L over here, this is going to be latent heat of fusion that you just saw before. Now, once all those ice completely melted and everything, now you still keep adding your energy. So it will just keep rising in temperature. So that's when you go from 0 and just get it hotter and hotter. But during this transition over here, of course, you can still use Q equal to MC delta T. You guys with me? So this is Q equal to MC delta T portion over here. But then the C that you are using over here is supposed to be C of liquid water. So you just have to use C of water over here. And then you hit 100 degrees Celsius. Now that is the portion that you know that you're going to get liquid water to vaporize. So you start vaporizing the water. So over there, then you won't see any temperature change anymore. But during this temperature here, the longer you add the energy to your water, more will get vaporized. More and more. So during this process, it's just ML again. But it's going to be vaporization. So it's a latent heat of vaporization, yeah? Until you do the complete vaporization of liquid water. So completely vaporize everything. So before that, it's just going to be the mixture between water and steams. But once you complete the whole phase transition, that steam will get hotter. So it's going to be superheated steam up there. So once again, if you reach this portion over here, you go back and use Q equal to MC delta T one more time. But this is going to be vapor now. It's a specific heat for vapor. That's going to be different value as well. Cool? All right, and that's complete the whole thing.
Okay.
That's my point. I hope you see the whole picture over here, and I think you have seen this, like maybe this is the 3rd time in your life or something. All right, but this conclude, or at least for those of you that haven't done this kind of business before, haven't done this kind of heat, transfer, heat, phase transition, or Q equal to MC delta T, I think this is a good summary of everything that we have done. Cool? All right. So that's it. Now the fun thing starts to happen right here. And we're almost done for today's lecture here, guys. So in reality, just using those Q equal to MC delta T and ML is just, okay, done. Everybody can do that. But the fun things will happen here when you have 2 parts of your system having different temperature and they are put in thermal contacts. Whoa.
Okay.
That's much more fun, right? So what you have over here is, let's say if you have a cup of water, okay, that's fine. And then somehow you dump in like an ice over here. Bam, in there. And everyone knows ice will melt a little bit or maybe all of them. Water will cool down Yeah, on and on. So that means what you can think of is like, hey, you have a portion of this that has a cold temperature. Let me call it a T cold. And there will be another portion over here that's going to be T hot. But then you put them in thermal contacts. When you dump in the ice, I mean, you already put them in contact. So I can actually draw this one as a diagram. Think of it this way. Oh, let me do the color coded here. That will help. Here we go. So you have, see, it's like you have two parts of your system. One's hot, one is cold. So you have T hot on this side. You have T cold on this side. And then, of course, you already learned from zeroth law of thermodynamics. When you put in thermal contact, eventually they're going to have energy transfer until you reach thermal equilibrium. So that means during this process, there will be a heat transfer from hot to cold. Everybody know this. Cool? All right, now here comes the point that I want you to take home today. Well, there's so many points to take home, but this one is just something that's last stuff that I'm going to sort of give it to you today is heat flow out from the hot part and enter the cold part. Heat flow out from one and flow in into the other. So if I want to quantify this one at Q, and let me call it a Q hot, and let me call the one that flow into the cold part to be Q cold. These two must be the same amount. You guys with me? Of course, but John, it's the same heat. It's flow from one side to the other side. So if I want to say they are equal in magnitude, I have to write it something like this. I put absolute sign here. Why? The reason I want to put absolute sign here because if I don't use absolute, how can I take care of the direction of flow? You guys start to see what I'm trying to get at here. Q hot, that is the outward direction, heat flowing out. But if you look at the cold side, heat is flowing in. So from now on, and we're going to use a lot next week, if you have an object and you have heat flow into the object, we're going to say you have a positive heat flow. Cool? You're adding something to your system or whatever you things that you are considering right now. On the other hand, if you take away some heat from it, so this means there's some energy that you're taking out, so this means there's a heat flow out, that has a negative direction to it. See? We need the directions because heat has two directions. It's either flow inward or flow outward from the system or from the thing that you are considering. So that's why if we want to take into account the direction, so it's going to look like this. Q cold, that's a heat flow in, must be equal to negative of Q hot. You guys with me now? Because we know they are the same Q. Let me sort of highlight over here. If the amount of Q just get pushed to the other side. But because of the sign, one is in, one is out. So you have to introduce the negative sign in the front, and hence this expression right here. Okay, the reason that it looks complicated at this point, even though it's just a negative sign, the reason is because next week, you have to be very, very careful with the delta T. I'm not stressing about this word just yet. Every time you talk about the delta T, and every time you have the symbol sigma, delta means change. So you always need to use the final minus initial all the time.
Okay.
All the time.
Okay.
All the time.
Okay.
Okay, that's very important. Why? Because think about this. If I start today with 100 baht, and let's say at the end of the day, I have 99 baht. So what is my change? Of course, if we speak loosely, you probably say, okay, my change is 1 baht, right? But that's not right in terms of the sign because my money is smaller. So I have to say -1 because it's possible that at the end of the day, I might have 101 baht, and that is +1. So there is a direction associated with the change all the time. So to be correctly speaking about the change, you always have to take the final minus initial all the time because you allow the negative change to occur when the final value is less than the initial. This will be super important in thermodynamics because direction is completely opposite, in and out. Okay, cool. All right. So the business of having the mixture between two unequal temperature like this, and especially with the water or with some things that, dealing with liquid and other stuff, it's under the topics of calorimetry. Okay, so calorimetry is something that you want to sort of like calculate the amount of energy flow due to the temperature difference. All right, this is like the oldest portion of thermodynamics study, or whatever, heat study back in our history of physics and all this stuff. All right, and the device that allow you to do this kind of calculation, or you might have done like physics lab, is a calorimeter. Okay, so that's fine. Okay, so this is some concepts that we can extend from the understanding of heat. Okay, and this is going to be the things that we're going to do next time, but at least I'm just gonna give this as just like a starting, just get things started a little bit, but then we're just gonna complete this problem next time, so you have something to think about here. See, this is the same scenario that I just talked about. You have a cup, you have 200 gram of water in here, so that's 200 gram, and you already given the initial temperature. See, so it's pretty warm water, 50 degrees Celsius. And then you have ice, ice right here. And you dump this ice, and of course, ice gonna start from 0 degrees Celsius, because this is not like a super frozen ice or anything, it's just regular ice. So you say that ice is at 0 degree. And then you have 500 gram of ice that you're gonna dump into this one. They'll just want to figure out what is the final temperature after you mixing these two together. This is the calorimetry problem. See what kind of problem you're gonna have to face here. All right, but it's simple, because what you're going to do is Q hot equal to negative Q cold, or if you want, the absolute of Q hot is going to be equal to the absolute of Q cold. So the Q cold is the cold portion of this one. It's cold. This is not cold here. That's cold here. This is a cold portion of that.
Okay.
And the hot one is the water right there. You want to put them in thermal contact right here. Cool. All right, so we are going to complete this problem together next time. So we're going to use this exercise as a starting point next lecture, and we're going to move on to other more interesting stuff as well. All right, guys, sounds cool? Having fun today, yeah?
Okay.
All right, guys, that is it for today. I'll see you guys next Thursday, yeah? Okay, bye-bye, everyone. Thank you.